All right, line I2. We're going to go through all three learning tasks for this one because they're also very closely related and really just describing the same thing. So this is going to be learning tasks 1 through 3, which are going to be describing surge protection, devices, ratings, and installation, which is supposed to say installation, but, I teach electrical because clearly I'm not here to win any spelling prizes. All right. Surge protection devices, or SPDs. We know that in current industry, even in homes and things like that, we've got a ton of electronics that are in part of people's day-to-day life. Computers, security systems, life safety equipment such as fire alarm systems, or a lot of our backup power type of systems, automation systems, communications, home entertainment, all sorts of stuff that's really expensive and can be really easily damaged. Because when we're looking at semiconductor electronics, a little bit of voltage across them can cause a whole pile of damage. So we've developed this whole class that is going to be called my SPDs. And SPDs are going to work off the fact that they are going to be a diversion path. I do want to, before we even begin looking at what an SPD itself actually is, just go over what we actually have inside of a circuit. We'll go take a look at a standard 3-wire Edison type of circuit over here. This is going to be what we have at our supply transformer. BC Hydro is going to go and supply the primary of the transformer. We don't worry about that. But then the secondary over here is going to get connected onto our system. Energy cannot be created nor destroyed. It can only go and change forms. And so what we are going to put in here are not going to be able to go and block values of voltage, but what they are going to go and do is find a way that they can go and effectively terminate those values of voltage, or drive those values of voltage back to some point where it's not going to go and cause any sort of danger. Let's take a look over here. This is normally going to be 120. This is going to be 120 as well. And line to line, we're going to have, 240. Coming out of my panel, we'll just draw this over here. We'll say that this section right over here is going to be my panel. So here's my main breaker on line 1. Going out and across. Here's my neutral connection right over here. That neutral is going to get grounded down. And then on my line 2, we get the same thing. We get our main circuit breaker. And then from there, my circuit breaker goes down to the subdistribution. And from the subdistribution goes out to all the rest of the loads. So we'll have our individual panel breakers that are going to be inside of there. These are going to be like the 50 amp, the 20 amp, etc. Those are going to be fed out to a bunch of different types of loads. That's the stuff that we're trying to go and protect. So what we want to do is we want to always cut off the current before it's able to get there. Now, energy cannot be created or destroyed. We have to find some way to go and divert it. And current is going to go and take the path of least resistance. So we do have resistance through all this stuff, the loads that are going to be connected there. What we can do is we can go and apply something else that is going to go and provide an alternate path. I'm going to just label this thing as being SPD. We'll cover over how they're made later on, but let's just go and take a look at what that SPD is going to do. Most of our SPDs are going to go across from line over to ground. Now, we don't necessarily see that they're just connected, line over to ground. What we usually see is that they're going to be 3-wire. What they're trying to do with that 3-wire, the one neutral wire that's going to be part of the component, is connect this thing back to the bond, which is then in turn going to be connected to ground. Because a lot of what happens is going to be stuff that is going to come from outside influences like switching transients or lightning strikes, and then it's going to go and try to divert to ground in a lot of cases. That's where lightning is actually trying to go. So if I take a look at my surge protective device, if for whatever reason we were to go and get some increase, that we have a lightning strike out here that hits my primary line, that's going to go and raise this value of voltage. It might have been at 12 kV. Now we're going to go and jump that thing all the way up to 25 kV. That would be low for lightning, but hey, we'll throw it in there. That would mean that this would jump up from, if that voltage over there doubled, this one over here would have to double to become 240, and this one over here is going to go and double to become 240 as well, which means that across from this end to this end of my transformer, I've now got 480. We don't want that to go and happen for any of our line-to-line or for any of our loads. So what we will do is we will go and have devices that are going to go and clamp. They're going to basically take a look at that waveform. So if this was my 480 volt waveform, what we should have had would have been at the same frequency. Oops, let me just draw that again. A 240 volt waveform at the same frequency What these surge protective devices are going to do is they are going to go and clamp at the peak. And what I mean by clamp is they are going to go and only let through what's up at the peak, and then anything past that, they are going to go and be able to divert to ground. Because if I take a look at this transformer, it wants to run its current through the path of least resistance, so it's going to be able to go and run some through there. Done through semiconductors, generally speaking. What we're going to divert through there is going to be this peak, anything that's higher than that 240. So, well, yes, we do have the transient that's going to be going on. All that our load is going to see is it's going to see for just a little bit there that's going to have kind of a squared up looking waveform. But the voltage value is not going to be any higher. And the frequency, where it starts, where it ends, is not going to change as well. Anything that is in the blue sector over here gets passed on to the rest of my loads. Anything that is over top of those values gets diverted through here and is run off. This thing will actually go and dissipate some heat. It's not designed to go and dissipate heat long term. It's only there for a surge, which means it's going to have momentary ratings for these things. We have had a couple of names for these things in prior iterations. SSA, secondary surge arrestors. Those are, generally speaking, talking about ones that would be on top pole lines, as well as TVSS, transient voltage surge suppressors. Those were, generally speaking, components that would be inside of components. Let's talk about where surges themselves come from. So this tells us what the surge suppression is supposed to do. It's going to just top the voltage off. That's all it's doing. It's beheading that, and it's discarding this through heat off of the surge protective device itself, and it's only allowing the good usable value of voltage to pass through these. Possible sources are going to be usually from outside, and they're going to be a transient. They're not going to be something that's considered to be always on the system. If I've got a voltage that is always on the system, I'm going to have to go and adjust my transformation ratio. You use a tapped transformer or change transformers altogether. This is for momentary stuff. Lightning strikes are a big one. Lightning strikes are going to raise your whole grid. Now, lightning is when we get clouds and air movement that are going to be turbulent, and it's actually picking up electrons, ionizing, and it's going to build up a big enough electrical charge, and all of a sudden it has to have this strike where, boom, the thing goes and neutralizes the amount of charge differential between the Earth and between the cloud itself. Massive amounts of electricity flow for that, split second that thing is going to go. So if we're close by that, all of that is going to get diverted. If that strikes and hits your hydro lines, which are elevated, sometimes they're the only elevated thing out in the prairies and things, it's going to run down through that, and then it's just going to go and scatter across our grid. It does attenuate as it gets further through the grid because every single piece of copper does have inductance. Remember, our simplest form of inductor is a straight piece of wire. So it will choke itself off, and it won't travel, for forever. But it can easily put a couple kilometers over top of the wire, that it's going to have no problem whatsoever. Utility switching is where hydro is going to be, switching grids to go and maintain. They do this all the time. There's consistent switching throughout the province as they are balancing load, diverting, power off to California and things like that. Electrical accidents can also cause them. This would be unintentional. This is going to be, where somebody has run their car into a telephone pole, and it turns out the telephone pole has got power attached to it as well, and you get a couple lines that short together or something. We can sometimes go and have lower energy surges that will come inside of our building that we ourselves will create by accident. Sometimes they're going to be off of components that work with high electrostatic voltages. So photocopiers or microwaves or laser printers are common places that, we will see these. The other ones are going to be my loads that are going to get driven. Elevators can sometimes go into overdrive, right? If your elevator is accelerating downward, it can overspeed the motor, and that can act as a generator on the system, raising stuff. We also have some loads that are going to, in and of themselves, have massive amounts of surge inside it, where they're literally moving fluids. Air is a fluid, so is gas. So blowers and air conditioning systems are all going to have that. And then the last one would be inductive kick. If I've got any sort of a DC rectification happening inside there, and I'm working with DC components, and I don't have a proper snubber or freewheeling circuit set up with that thing, then I am going to go and, boom, whenever I shut the thing off, I'll get a DC kick back into my system. It's all for temporary things. Two main compositions that we are going to go and have. Two, I guess it is kind of three. We have got, resistive, and we have got semiconductors that are going to be utilized for these. Zener diodes are something that you would have covered inside of, it would have been first year you would have covered Zeners. And it's basically a type of diode that's going to maintain a specific value of voltage over top of its output. Now, a Zener diode does always need to have a bleed-off resistor that's going to be in line with it, right? Because if the Zener is going to hold its value of voltage, you need somewhere to put the other value of voltage. These surge-protected devices are going to incorporate that, and it's going to be a high wattage one, so it can just bleed that off relatively quickly. Avalanche diodes are another type. It is a type of Zener diode. They do conduct at a reverse bias voltage level. So like a regular diode, you can forward bias and you can reverse bias them as well. But they can tolerate massive amounts of let through, more so than a Zener. A Zener is regulated. It's got like just a max amount of current. These other ones are designed to have surge current that goes through. Thyroid SPDs are going to be a form of resistor. It's going to be a type of material that exhibits inverse resistive characteristics. In other words, when my voltage is low, it is going to have a high resistance. And when my voltage is high, it is going to go and have a low resistance. So if you could imagine that this surge protective device was a resistor that is going to have a high value of resistance. Let's go and say that this thing is going to be, 500 k ohms, 500,000 ohms. There will always be a little bit of current that will travel through this at 120 volts. We'll go back to our system into normal. So normally, yes, we will get a tiny little bit of current that's going through there, but it's really not that much because when we look at it, it is I is equal to E over R. So 120 over 500,000. Oh, that's one too many. Gets me to 240 milliamps. Tiny amount of current that's going to be going through there full time. So there will be a little bit of heat. It's lost to the system, but that's all right. You pay to play. We're protecting the system itself. When I go to a higher value of voltage, based upon the construction of this, I can go and set it to go and trigger at, X value of voltage, 170 volts or something like that. If it hits 240 volts, what will actually happen is its resistive will have dropped. And in that case, the resistance might be down to like 8 ohms or something like that. It's a really drastic drop when these things go into conduction. So now it's going to become, 240 over top of 8 ohms. And so it's going to be able to go and pass all of that surge current through it. Massive amounts of surge current that it will drive through it. It does drop our overall voltage. It doesn't maintain our voltage on the system, which is why we don't always use thyroid for it. It's really good because it can drop so rapidly and it can dissipate so much. But what it does is, as soon as it goes to low values, it will not maintain our system voltage over top of it. So all of these loads over here are going to get browned out. Brown out is simply where my voltage drops away. So you just see that off of them. You get the strike. The strike doesn't go through, but everything does shut off and has to come back on. It's annoying, but it's better than stuff blowing up. Thyroid arrestors are often used for lightning arrestors. You'll see them on the side of poles. They're going to have a connection that is going to go directly between the actual high voltage line. Just erase this and get about myself a little bit of drawing room here. So here's my pole arm up at the top there. And then I'm going to go and have my high voltage lines that are going to be going across. And what you'll see off of these is that there's going to be a stinger that's going to come off by the pole. And then it's going to go down to a tubular type of device like that. That tubular type of device is then going to go and have a ground conductor that is going to go and run all the way down. We'll stick it behind a guard so it doesn't get ripped off or anything like that. But what that is a stack of thyroid discs inside of that tube over there. It is constantly connected to ground. There is milliamps of current that is going to go and be traveling through it. There has to always be milliamps that are going to be traveling through it. You will see that these are going to be well protected as well because they do provide a continuous path. If somebody were to open it, cut this thing away, they would be exposing themselves to high values of potential voltage. Not a lot of current, but they could be exposing themselves to 25 or 12 kV or whatever my distribution lines are at that place. So we see these on the side of poles. They're just designed that they're going to be having a trickle of current going through all the time. And then when lightning strikes, boom, it's going to go and travel through this to ground because that's going to break over really quickly. We'll sometimes also have them connected across the primary windings of our transformers, which would mean that if this was a hydro transformer over here, they can sometimes actually have these things built in so that that thyroid resistor is just going right across this. So that if there would be a voltage spike, this is going to go into conduction, which drops the value of voltage, which means that I'm not going to transform that value of voltage through to the other side. The MOV, or metal oxide varistor, is going to be a semiconductor component where we are going to go and use special chemical reactions to create a proper type of oxide that's going to act as a insulation. It acts in some ways similar to a diode, in some ways it acts similar to a transistor. We won't go into them. They're cool, if we get around to them inside of our 3rd or 4th year, we might deal with them. They're not part of our curriculum yet at this point, but they've always talked about putting them inside there. But it is going to go and be a semiconductor component that is going to go and trigger. We build these things specially. Once we bring these up to a trigger voltage, they're going to go into conduction. It is not a resistor the way that thyroid is. It's a semiconductor that's just going to go and drop its depletion region at that point. So it will wait till we hit our value of voltage. If this was what it was over here, we could think about this thing as if it were back-to-back diodes in a lot of cases. Just draw that in over here. So one of these would always be blocking. But these things are going to be back-to-back diodes that are going to be blocking until we hit a breakover. And at that point, then boom, they're going to go and shove current through them. What they will do with the MOVs is they are going to be similar to a Zener that they'll maintain a voltage across it. So they are going to go and do clamping for us. Clamping is different than diversion. Remember that my thyroid is going to drop my value of voltage. Anything that clamps is going to just chop off the top of a bad waveform, and it is going to go and clamp or hold that voltage level. If we are looking for 120, it is going to go and hold 120. The waveform might be distorted, but it's going to keep the voltage level correct over there. Most of my surge suppression is going to go and use these. It still maintains voltage on my system. We don't have brownouts on the system, and they do tend to be able to last many cycles of having to charge and to allow charge through and to then to go and block again. Okay, let's go into learning task number 2, which is going to talk about how we describe the ratings off of these. Okay, they're not going to list every type of rating that's going to be on these. A lot of these are going to be found by going to manufacturers' websites, and one of them that's on here is not the correct rating. So let's just go through what's inside of the book. The first one that they have over there is called the MCOV, the Maximum Continuous Over Voltage. And they say that this is the AC or DC voltage above which the SPD will provide clamping. This value is chosen according to the rated nominal voltage of the system. There's a typo inside of that sentence. It is above which the SPD will not provide clamping. What they mean by that, and I'll just erase a whole pile of this right now so we got some room. We know what clamping is at this point. That's maintaining our voltage level and burning off any extra voltage. We burn it off as heat over top of our SPD. But this one over here, we're going to go and graph our voltage ratings just really quick. We're going to say that this is going to be a value of 0 volts. We're going to say that we've got a 120 volt surge protective device. So this is going to be a value of 120. We are going to go and call that thing the nominal value. That's where we want our system to go and be. Then above that, we are going to go and have a range that it's going to be able to go and take care of. And then this peak over here is going to be my MCOV. Now this thing could be quite a ways up over there. Let's say that this one is 2400 volts over there. What this is, and you should have added that word not, is the AC or DC voltage above which the SPD will not provide clamping. In other words, if I get a surge that comes through that is anywhere between 120 to 2400, I can clamp. I can cut off all that excess voltage that's in between there, and I can clamp to that. However, if I exceed the MCOV, if I'm above there, let's go 2500, that's where this thing no longer works. It's the maximum voltage rating. Okay, the voltage protection rating is going to be what I'm actually targeting. So for this one over here, my voltage protection rating is going to be based upon, the maximum that's going to be inside of its class. Now they do have standardized levels, and they will be higher than what our nominal voltage level itself is actually going to be. This is 120 over here. What I might use off of this one is obviously not going to be 120, because then I would be cutting off the top of my sine wave, right? We know that we need to have 120 divided by 0.707, which is going to get me to 170 volts. That's going to be my peak of my AC sine wave. So my peak of my AC sine wave, if we were to go and double that one, we'll just do 17 twice over there. We end up at a value that is going to be 330 over here. or 340 over here. This is going to be what they refer to as the nominal 330, their standardized level. So I would be using one that's going to have a 330 because it's looking at, it is going to clamp anything that goes above the peak in one direction or above the peak in the other direction. That's where they're getting that nominal rating of 330 volts. They're just looking at, how high my sine wave is going to go above each one of these. In reality, it's going to be a little bit higher than that. Yes, we are above 170, but that 330 rating is just a standardization. It's like how we say, 115, 230, or, 125, 250, or 120, 240. We're referring to the same thing. It's a nominal system type. Surge current rating is going to be rated inside of kiloamps, and what I'm going to go and have in with a surge current rating is just going to be how many times I can surge through this thing. What we get is total amount of current, and we've talked about, transformer fault current that we can go and have. Part of, what we get inside of here is not so much that we're looking to deal with transformer faults. It could be, but we're dealing with just large amounts of fault current that's going to go through. 20 kiloamps is just going to be the maximum amount of fault current that it will let through. Now, if I go and have something that's got a 40 kiloamp let through, all it means is it's got more paths inside. They're just placing more parallel elements inside of it, so it can go and do that more often. It's not going to burn out nearly as quickly. Short circuit current rating is going to go and be the maximum size of my short current circuit current that the component or assembly can withstand. Nominal discharge is going to be the peak value of surge current that's going to get conducted through. There will always be a little bit that gets through, but we're not going to allow all of it through. It takes a little bit for even our electronics to go and react. And then after that, we're then going to get into different types of categories. And category rating is something that you should be familiar with at this point, hopefully from meters. Every meter has got a category rating. It's a different category rating that they are working with inside of meters than what we're working with here, but it's a similar type of idea. We're talking about the level of exposure that we could possibly go and have to surges. So we'll start out over here at my pole line. I've got high voltage lines that are going to be coming in. Those high voltage lines, I'm going to go and take them down to a transformer, pole top mounted transformer over here. And then from that pole top mounted transformer, I'm then going to go and feed over to an installation. We'll just draw out an installation over here with a weatherhead on the side. Let's take a meter base like that. And then we will go feed in from the meter base and we'll take that thing into a fusible disconnect. Oh man, that one's terribly drawn. We can do better than that. Draw it like that. And then from there, we will take that thing into a actual panel. Here's my panel, etc. Then from there, we obviously subdistribute, with our electrical systems, and then we will go out to our actual load. We'll go and draw this one over here as just being a receptacle somewhere downstream. So let's go and draw our lines in. This is going to be what we would refer to as a category C type of location that I'm going to go and have. Category C is going to go and be outdoor and service entrance installations. Cat C over here. Category C is going to be obviously high danger because anything that is going to be like lightning or anything like that is going to be probably directly connected to it. So it's going to have a fairly high withstand rating. Remember that as we go further and further through our system, and especially as our wire gauge goes down, we're going to go and see more and more counter EMF or inductive effects that are going to go and prevent surges from getting all the way through. So we've got our category C out there. Then we're going to go and have category B, which is going to be for feeders and distribution. Category B is going to be everything that is inside of blue over here. That's going to be my, other than the building, but my category B that I'm going to go and have. And then category A are going to go and be any of my runs out to my components. It has to exceed 10 meters from the B. So this thing over here has to be at least plus 10 meters. And it also has to be at least plus 20 meters from here. The reason we've got these length restrictions is, once again, the inductive choking effects that we are going to have of our wires. It is going to be my least dangerous type of category that we are going to have. We are also going to go and have typing that we are going to have. So these are my categories. This is the, you would choose. I'm going to have something that needs to be connected out here on the lines. I'm going to have to find something that's going to be for a category C, I'm going to have something in the panels, it's going to be category B. I'm going to have something that's going to be out of the load, that's going to go and be my category A. All of these category ratings, by the way, are found inside of your Canadian Electrical Code. If you go into section 26, from section 26, 420, which is the rule that you would be at low voltage surge protectors, it says, except as provided for in subrule 2, where low voltage surge protector devices are to be connected to a consumer service, they shall be installed indoors at least half an inch, 12.5 mil from combustible material, and they should be at the service head, the point of supply and the overhead distribution, the load side of a socket or outdoor distribution enclosure, and they're permitted to be connected to an overcurrent branch or to a branch circuit supplying utilization equipment in the building. It just talks about how we connect those things up. But then if you go to the Appendix B note on that one, they then go and give us our different classifications, same as what we have inside of here. And then they also go and talk about the typing. So category is where we're going to go and locate them. Type is going to be the type that we place inside of those categories. Looking at this chart over here, table B26.1 over here, tells us about the different types of surge protective devices. We are going to have a type 1, which is going to be permanently connected between the secondary side of the service transformer and the line side of the service equipment, and it's good for categories A, B, and C exposure environments. So that's talking about location. This one over here, if I go back, this would be category C, and I could go and place a type 1. A type 1 device is allowed to be placed inside of a category C, between the secondary side of the transformer and between my actual components over there. I'm also, if it's good to be able to go out here where there's lots of danger, it also tells me that I'm also allowed to put it into Cat B, and I'm allowed to go and put it into a Cat C. We would just be overprotected at that point. If I take a look at a type 2 is going to be downstream. So type 2. A type 2, I can go and connect downstream over here at my service. So it's on the load side. It could not be ahead of here. It would have to be somewhere downstream of that actual first bit of fusing that I'm going to go and have on the system. I can connect them into there. They do have a little bit of an errata inside of your binder over here, where it talks about that it's a variant that most homeowners purchase if wanting to have surge protection on existing residence or whole home surge protection. They refer to it as a type 3 inside of there. It is going to go and be a type 2 over there. So inside of that paragraph, just list that thing is going to be a type 2 type. That's going to be, mounted. Usually we just see them. They're going to have a little nipple that's going to be attached to a chunk of flex, and it's going to get mounted to the side of the panel like that. Type 2 is allowed to be used over here. Type 2 would also be allowed to be used inside of a category A, right? It's good for a category B. It would definitely be good for a category A type of location. Looking at these over here, I can use anything that's type 2 in an A or a B. And then last of all, if I go down to type 3, it is going to be cord connected or direct plug-in types, what we refer to as a power bar inside of our day-to-day. And it's going to be receptacles that could be connected to it, and it's only going to be for category A. Anything that's going to be with that 10 meters of cord providing the inductive choking. The rest of these over here are just components. They're not intended for field installation, In other words, the stuff that we are going to go and have inside of our types 1, 2, and 3. The components that go inside of a 1, 2, and 3 could be either a component 4 or they could be a component 5. Component 4 is assemblies, so a bunch of components that are placed together into a complete circuit. Component 5, or type 5, is individual discrete sections of that assembly. So if I take a MOV and then I form it into a circuit, that would become a type 4. If I take that type 4 and I build it into a power bar, that would then become a type 3. That's the way that they're trying to go and lay these out. All right, let's go and take a look at the last little section over here on inside of our binders, which is going to be now looking at the pretty pictures. We've been waiting to get all the way up to here. Learning task 3, which is going to describe installation of these. Cascade surge protection is a common way that we are going to go and deal with this. Cascade surge protection is where I am going to, as I work throughout my installation, I'm going to have multiple surge devices. I can have a surge device over here, somewhere out here that's going to be Cat C type 1. I can go and have another surge device, would be hanging in the middle of the line. Why don't I place it by something here? We'll put that thing right up there. I could have a type B that's going to be somewhere over here. We'll make it type B. And I could have another type C that's going to be a plug-in type that's going to be all the way over here inside of my category A. What I would get is I would get a continuous attenuation of the amount of let through. This thing cannot prevent everything from going and getting into the building. There will be some let through, but that bit that's been let through then gets, once again, whittled down by what I've got inside of here, which gets whittled down inside of here. We call that cascading our protective devices. So if I had something really, 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 valuable, I don't know, let's say that you had set yourself up something, you were farming Bitcoins. You don't want that thing to get taken out by lightning strikes or anything like that. You lose the hard drive, you lose the Bitcoins. Good luck. So you want to go and, protect this thing. So you would want to have a cascaded type of event that you are going to have. Type 3s, which are going to be, my real cheesy type, they're going to be the ones that look like this. Generally speaking, just a power bar that we will go and plug into stuff. Type 2s have to be hardwire connected. This over here is just the corner of a panel. The rest of the panel is up top there. We don't see it. But this thing is going to be nippled directly into. Most of them are going to go and have those threads right on the top. So we mount this thing up against the side. Some of them come with a little flex run. Other ones you will see, they look like circuit breakers themselves. And they actually just plug on. So if you took a look at them, they would look the same as any other circuit breaker. You're going to have that set of jaws at the back. A set of jaws there, another set of jaws there. And they will have a neutral connection, but they won't have any other screws on them. But you plug them into your panel. You take the panel cover off, you plug these things in, you connect this down to the neutral inside of that panel, and now you've got whole home, surge protection. You'll have a couple of LEDs on them as well that are going to usually indicate what statuses are going to be. This one here says Type 2, surge protected device, AC power protection, indoor or outdoor type of use that I'm going to have, and then it's got 2 status indicators. These are green lights. Those are not green lines that are around the outside over there that are going to indicate whether this thing is good, whether it's, had damage. They do self-monitor, most of them. Type 1 surge protected devices, they don't have any pictures inside of here, but they're going to be bigger ones, usually supplied by the utility because and I know that anything between here, the weatherhead, and over here, that's all owned by the utility. So they'll be the ones that are going to go and have that there if required. Usually not for standard residential applications, but for commercial or industrial, we could absolutely expect to see them. All right, that is the end of surge protected devices.